All right, hope everybody had a good break. Nice little break there, a little vacation for you. Well, Braylon smiling ear to ear because his Wolverines won over the weekend. Everybody has to smile ear to ear because the Browns won and the Bengals won. It was a good weekend for in the Ringer household, wasn't it? You got the Wolverine. You know what? I'll be quite honest, and I hate to admit this because I'm not a fan of Jim Harbaugh, but he out-coached Ohio State. I was not impressed by the product and the results of how Ohio State reacted. But yeah, that's what it is. So I hope everybody enjoyed their time away. We have quite a bit still to cover. My goal, once again in this classroom, my goal is to get to the final before we go to break, before Christmas break here. So that is what I'm going to try to achieve, but we need to push ourselves to get to that point. So we can have the final before Christmas break. We come back from Christmas break, we'll have a project to do. And once we do the project, that'll be the end of the year. So I don't want to keep things to after Christmas break for the final if I can. So I will try to continue to push. Last week or 2 weeks ago, whenever it was, 10 days ago, a long time ago, it seems like, we started talking about confidence intervals, the idea of confidence intervals. You should have some notes here that I already handed out. And we talked about the election, what happens with the election. What, once again, statistics do is they take a sample and they try to make predictions about the population, because they're not going to poll the entire population to see who they're going to vote for or who they're not going to vote for. Okay, but they can pull a sample, and what these samples were is about 1,100 and about 1,500 samples to see who they were going to vote for. Okay, with that sample, they would sit there and make a prediction. This is your sample right here, the sample statistic. But we have what is called a margin of error, which is plus or minus a specific value. Okay, and once again, as we talk about this, we're going to be correct to a certain point, but we're going to be plus or minus a specific value. Well, this idea right here is what is called a confidence interval. They were, I would probably guess, they were 99% confident that the percentage that was going to vote for certain people was between these two values and those two values. They were 99% confident. Okay, and that's what they want to be able to do. They want to be able to make predictions with respect to looking at a sample. Okay, we started talking about a point estimate. We talked about parameters, point estimates. Point estimate is a specific numerical value. Best point estimate for a population is a sample mean. And we looked at the idea of a dog, how much it costs to raise a dog up to age 11. Okay, so we could take a sample of this and then try to predict out a population. 3 properties of good estimator. Estimators should be unbiased. Estimators should be consistent. Sample size increases the value of the estimator approaches a parameter. And estimators should be relatively efficient. Best estimators have the smallest variance. And that's where we stop. Once again, I will ask you, what is the characteristic of...
Dude, they've been off for a week. Can you ease your way back into it?
That's funny.
What do you mean? Look at them, they're like, they have turkey-itis.
I don't care.
They're, all your words are going up in the air into that cloud thing that there is, and just out this door. And they're not getting any of it.
Well,
Tell him to slow down.
I don't know. There's no way he's slowing down. We had 2 days off last week that we slowed down.
Okay. Hey, good to see you guys back.
The average vehicle registered in the U.S. is 8 years old, or 96 months. Assume a standard deviation of 16 months. If a random sample of 36 vehicles is selected, Find the probability that their mean age is somewhere between 90 and 100 months. What we're doing is we're going back to what we did in the previous chapter. We have a sample mean, or we have a population mean of 96. We have a standard deviation of 16. We have a sample size of 36. We want to determine the probability that their mean age is somewhere between 90 and 100 months. So what we're going to have to go back and do is we're going to have to go back and look at the idea of a z-score in our z-table. Just as a review, how we calculate our z-value is our sample mean minus our population mean, standard deviation divided by the square root of n. So we need to find a z-score for 90, and a z-score for 100. So we need to find two z-scores here, one for 90, one for 100. Once again, this goes back to what we did right before break. So we have 90 minus 96 divided by 16 divided by square root of 36. Find your two z values here. Find your two z values. We're going to then go to a bell-shaped curve. Find your z values, check those values with somebody around you. Then place them in a bell-shaped curve. Go to your z-table, find your values from your z-table. Once again, this is all what we did. This is a little bit of review of what we did prior to break. Our last test that we did dealt with, we're dealing with the central limit theorem here. Working with the central limit theorem. Finding our z-value with the central limit theorem. Once again, find your z-values, check those values with somebody around you. Place them on a z-table or a bell-shaped curve. Bless you. Everybody get for your z-scores? What do you get for 90?
Negative 2.25.
And for 100?
1.5.
Okay, so we have negative 2.25 and 1.50. So here's our values. We go to our z-table. Go to our z-table. From our z-table, we can calculate areas. Isaac, what do you get for table value for 2.25
.4878,
and 1.50?
.433.
Now we want to figure out the probability that the mean is between that, which is once again connected to your area. So connected to our areas. And just what do we have to do with our two areas here?
Add them.
Add them together. 0.4878 plus 0.4332, and what do you come down to?
0.9174.
So if I would take 36 cars, 36 registrations, there's a 96% or 91% probability that it's going to be, the registrations are going to be, the mean of the registrations is going to be somewhere between 90 and 100 months.
I got 92.1.
92.1 when you add them, same values.
That's what I got.
92.1. Is that better? So we have a 92.1% chance. If I would take 36 cars and take the mean of the 36 cars, there's a 92% chance that their registration is going to be the mean of their registrations going to be anywhere between 90 and 100 months. So this is the percent probability the mean sample is between 90 and 100 months, 92.1%. But what we can also state, it can also be stated as a percent confidence that the mean lies between 90 and 100 months. So we can have a percent probability, but we can also talk about this as a percent confidence, how confident we are. I'm 92% confident that if I would take 36 cars, I'm 92% confident that the mean of those 36 cars is somewhere between 90 and 100 months. We have an interval estimate. This is a interval or a range of values. An interval or range of values to estimate the parameter. Once again, we are trying to estimate the parameter here. The parameter is the population. This may or may not contain the value of the percentage or parameter being estimated. But we have an interval estimate. We want to get a range of values. And we want to say the population is going to be somewhere between these range of values. We're 92% confident that the population is going to be somewhere between the values of 90 and 100 months. But as we looked at the election results, we were in between two range values, but we were in between range values, but it wasn't exact. So it may or may not be there, but it's a prediction value. Once again, these are prediction values. These are your FanDuel values that you're sitting there looking at, or your Fantasy Football League values that you're sitting there looking at. Okay, those are just predictions. And they're 99% confident they're going to be in there. But you sit there and say you're 99% confident, doesn't mean somebody can't get hurt the first play of the game. And they get 0 points for you. Then you lose the Super Bowl. A confidence level. It's a probability the interval estimate will contain a parameter. Assuming a large number, once again, this law of large numbers continues to come back for us. Assuming a large number of samples are selected, an estimation process of the parameter is repeatable. the first example, I'm 92% confident. Why? Because 92% of the data values are going to lie in there. Not all 100% of the data values are going to lie there, but 92% of the data values are going to lie there. All good estimators, all good experiments are repeatable. Sir Fig Isaac Newton says this ball is going to drop and accelerate as it moves downwards at 9.81 meters per second squared. I don't believe him. I thought he was full of baloney. So I did an experiment that proved that it's 9.79 meters per second squared. And I did the experiment over and over and over again. And I get 9.79, 9.81. What I have to do then is take my process and give it to every scientist in the world. And that process should be able to be repeated by other scientists and get the exact same value, 9.79 meters per second squared. Okay? They should be able to repeat what I did. If you're over in chemistry lab, she makes you write down a procedure. The reason why is if you find some findings that are different than normal, then somebody else should be able to repeat that process. The confidence interval is very similar to a confidence or interval estimate. These two are very similar. The specific interval is specific interval estimate of a parameter determined by using data from a sample and by using specific confidence level of estimates. Once we get into what we are dealing with here, and you'll have all these things in like a matching vocabulary section, but once we get into this, this is probably going to be the easiest thing that we do all year long. Because we're going to be doing the exact same process over and over again. We're just going to be changing a little bit of how we're handling it. And are we going to be dealing with a small sample size, a big sample size? Are we going to be dealing with a population proportion like we did with the percents? Or are we going to deal with standard deviations? What we will be doing, we'll take a sample size n. We will calculate an interval using z-scores to illustrate a confidence level that a population mean will be somewhere between or somewhere within the confidence interval. So we'll take some sample size n, look at the sample mean from that sample size n to estimate, and using z-scores to estimate a confidence interval for the population mean. Once again, most of the time, as you know, if you haven't realized yet, most of the time when you get in this class, we have all this new information that we're providing to you that you've never, ever, ever experienced. And it seems confusing at the beginning. But as we start going into the problems, you'll see the difficulty level continues to decrease because you become a little bit more confident and comfortable with what we're dealing with. Most confidence levels, most of the ones that we are dealing with are 90, 95, or 99% confident. And if you're 99% confident that something's going to occur, you feel pretty good about that. That's 1% confident that it's not going to occur. If you're a betting person, a wagering person, if you had $20 of your own money and you're 99% confident that if you put a bet down, you're going to win $20 back, so you get $40 in, you're probably going to do it. All right, let's take a look at some problems here. Population average salaries for teachers. In Ohio, it's $41,000 with a standard deviation of 1,500. What's the upper and lower bound salary for that would encompass 90% of the salaries? Once again, this is going back to what we dealt with already, problems that we've already did. We want this to be 90%. Okay, remember what we had to deal with before. Value is equal to mean z-value times the standard deviation. This boundary value that we're dealing with. Well, this is 90%, and what we did is we broke this down to 45%, 45%. And then we transferred that into an area. So we had 0.45, 0.4500. And then we went to our Z table and looked at the body of the table and tried to find 0.4500. The problem we ran into, the 0.4500, is halfway between 1.64 and 1.65. And I told you when we dealt with this before, if this would occur, I'd accept either value. Okay, what I'm going to tell you now, and we'll look at a table a little bit further down, is we want to use 1.65. We want to use 1.65 as this value. And once again, we're going to go to a table at the bottom of this page that will give you that. You're not going to have to memorize that. So to find our value, we take our mean, which was 41,000, our standard deviation, which is 1,500, and our z values, and we found these boundary values. So we have mean, standard deviation, and z value. So we have the 41,000 plus the negative 1.65 times 1,500 41,000 plus a 1.65 times 1,500. And we're able to find these two boundary values. Jamie, what do you get for the values?
I got 43,400, and for the second one, which is negative, I am 38,600.
Here we go with those values. Seth, you go with those values? What do you got?
30,525, 50,475,
What did you get for the first one?
38,525,
38,005 what?
25,
And what do you get for the second one?
43,475.
Is that better? We go with that? All right. Check your clicker clacker. So we are 90% confident. If I would choose a teacher at random, I'm 90% confident my range of values is that teacher's salary is going to be somewhere between these two values right here. Should that be 38,000? 525. Yeah. I'm 90% confident that a person's salary is going to be somewhere between that range. But what we want to take a look at is the idea of a sample population sample mean. Now what we have to remember is when I'm taking a look at the standard deviation of a set of sample means. Okay, that's equal to standard deviation divided by the square root of n. So if we take a look, when we start to transform our equation, our standard deviation is going to take a look at the idea of the sample means. Our population mean is going to, once again, what we're looking to try to estimate here is we're trying to estimate a population mean given a set of sample means. So our value, this is what we're trying to estimate right here. This equation gets transformed into this, which gets transformed into this. So to calculate a confidence level for a specific, given a specific sample, we can calculate these boundary values by looking at x bar plus the z value times our standard deviation divided by the square root of n. So this equation here just gets transformed into this when we have a sample mean. And that's looking at, once again, if we look at our z-score is x bar minus mu divided by standard deviation divided by square root of n. I can multiply by my standard deviation square root of n and then add my population mean. But what I'm going to do is we're going to look at our sample mean, because what we're trying to estimate here is our population mean here. Okay, a sample 40 teachers is chosen from a population of Ohio teachers. Their mean salary is $41,000 with a population standard deviation of 1,500. Find the confidence interval for a confidence level of 90%. we're doing the exact same problem. We're still looking at the idea that we're working with 90%. We still have a 0.4500, a 0.4500. We have a 1.65 negative and a 1.65 positive. Everything is the same, except for now, we're looking at utilizing this boundary value for the population mean is X bar plus our Z times our standard deviation divided by the square root of N. How we calculate this boundary value just gets transformed. Just like when we're dealing with essential limit theorem, it gets transformed. So now we have our 41,000, our negative 1.65, our standard deviation, which is 1,500, divided by the square root of 40, because now we have a sample of 40. So this boundary value, once again, just gets altered how we calculate this boundary value. Okay, Miller, what do you get for our two values?
40,608.67.
What was that?
40,608.67. And then 41,391.33.
So we are 90% confident that our population mean is going to be somewhere between these two values. Confidence interval CI is typically 90, 95, or 99%. We have an alpha value, which is the amount of two areas in the tails. So our alpha values here, this would be 5%. This is 5%, or 0.05, or 0.05. That's the amount of area in your two tails that you're not working with. So our population mean, our confidence level for our population mean is going to be somewhere in between our sample mean, our z for the confidence interval, minus our z for confidence interval, standard deviation divided by square root of n, and then the exact same thing, but we have a plus in there. The key is this table at the bottom. If we have a confidence interval of 90%, the z value that we're going to want to use is 1.65. If we have a 95% confidence interval, the z value we want to use is a 1.96. If we have a 99% confidence interval, our z value that we want to use is 2.58. Once again, knowing these values right here, it eliminates you having to do this every time. Saying that is 99%. Okay, this is 99%, which means it's 49.5%. You don't have to go through that each and every time to be able to do these problems. Utilizing this table right here, if you're given a confidence interval of 95%, the z value you're going to want to use is 1.96. If you have a 99% confidence interval, your z value is 2.58. So you can go to your table here. So when you're asked in a problem, in problem number 1, a sample of reading scores of 35 fifth graders has a mean of 82. Standard deviation of 15. Standard deviation of 15. Calculate the 95% confidence interval. I don't have to do a bell-shaped curve anymore. I could just utilize this here, my 1.96. That's my z for my confidence interval that I'm going to utilize. You're given the sample mean of 82. You're given a sample standard deviation of 15. And you're given a sample size of 35. And I can pull my z value from this table right here. So I have 82 minus this 1.696, 15 divided by square root of 35, and I do the exact same thing over here and make it a plus. Once again, the calculations are not very difficult, and this we will continue to utilize over and over and over again. Solutions to your homework are posted. Okay, if I have time, I'll look at going over some of the notes on the back page there. We'll look at that also tomorrow. We'll also get into what is called a t-value if our sample size gets smaller than 30. No bells today? Adios, have a good day.